Welcome to DCL 104. This is part 2 in my talk about inductors, inductive reactance. Essentially, we're going to talk about coils. This video, unlike most of mine, will be loaded with formulas and math. The good news is the math is going to be way easier than you thought, and yet more powerful than you might think. In other words, I think you're going to get a lot out of this. I hope you do. First things first, the vertical antenna loading coil I talked about was for 17 meters, not 20 meters. I wanted to state that right at the start because I'm going to talk a lot about it, and I didn't want you to think you'd heard something wrong or be confused. I was the one that was confused, not you. Now, two things we won't talk about. I'm not going to talk about straight wire inductance or impedance. It's taking on too much at this point. We will come back to both of these topics after we finish inductors and after we finish capacitors. We'll talk about impedance, inductance in the straight wire, and things like that. So what am I going to talk about? I want to do a very quick math review just to illustrate a little point. Then I want to show you how to calculate the inductance of a coil. Then I want to define inductive reactance and show you how to calculate it. And by the end of this video, you should understand how inductive reactance and inductance really works. You should be able to calculate it and describe the difference between inductance and inductive reactance. All right, let's do a quick review. You're probably somewhat familiar with Ohm's law. On the right, you have E for electromotive force. We measure that in voltage or volts. Below it is resistance, which is measured in ohms. The result of the relationship between those two tells us what the intensity of the current will be. In other words, it tells us what the current measured in amps is going to be. Let's say I have 12 volts. It's across a 12 ohm resistor. That gives me 1 amp of current. Now, watch this. If I double my voltage, notice that I doubled my current. Now, let's go back where we started. What if I doubled my resistance? Now my current drops. So this is lesson number 1. Any formula you look at that looks like this with something above and something below, always remember, if the number above goes higher, the result goes higher. If the number below goes higher, the result goes lower. That's all I wanted to show you. I'll come back to this concept in just a minute. Now, I want to talk about solenoids. Solenoids are a special kind of coil. We don't wind a solenoid for its inductance, usually. Usually we wind a solenoid to take advantage of the magnetic field it generates to do something with that field. But for the purpose of our discussion, let's just figure out if we can calculate the inductance of a solenoid. And then when I show you RF coils, you'll really see the difference. And the difference is relatively simple. Now, this formula is not the simple one I told you about. We're going to get to that. But I wanted to show it to you because it illustrates my point I made in the mathematical review. You're looking at this formula. You don't know what all the numbers mean. So the first thing you're going to do is find out what the numbers mean. Now, the first thing is, this is for solenoids only. This formula has nothing to do with radio for the most part. You're never going to use this formula, I'm sure. But let's play around with it a little bit. As I said, if the number above, and remember, this is this times this times this. If any one or more of these numbers gets bigger, this whole number gets bigger, you have more inductance. If this number gets bigger, you have less inductance. So, what are these numbers? Well, this is the permeability of the medium. What that means is how well does the area inside the coil loops conduct magnetic lines of force. The better it conducts them, the stronger they'll be, and the more inductance you're going to have. If you increase the number of turns, you'll have more inductance. If you increase the area of the turns, that means make the coil bigger, the loops bigger, you'll get more inductance. But if you stretch the coil out to be longer with the same number of turns, you're going to have less inductance. I pulled an example out of a physics textbook. The example was for a coil 40 millimeters in diameter, wound around air, so an air core coil. It's a half a meter long with 2,000 turns. I put the English equivalents up here just for convenience, because you'll notice my formula insists on measurements in meters. So we know that if any of the numbers on the top get bigger, we get more inductance. If the number on the bottom gets bigger, we have less inductance. What we also know is if you've got a coil of 2,000 turns that's only 19 inches long, you are using extremely thin wire. Well, the thinner the wire is, the more inductance it has. In radio, we generally never use wire that is that thin. Our coils look more like a coil of wire or a coil of copper tubing. So again, this formula won't work in radio because in radio, our conductors are thicker, so the adjustment factor that is hidden in this formula has to be changed. But let's just take a look at this. How would you do this math? Well, first of all, we have some decimal equivalents to convert things to meters, but the problem is, well, there's a couple of problems. First of all, we have to go look up the permeability of air. So we plug that into the formula. The next problem we have is we need the cross-sectional area of the coil in square meters, but we don't have that, do we? Well, we can create it, or we can calculate it. Because the cross-sectional area is the radius squared times pi. So we plug all of this into the formula. And what do we get? We get 0.0126 henries of inductance. Another way to say it is we have 12.6 millihenries of inductance. That's quite a bit of inductance. But is it really that much? Think about this. This coil I just told you about, it's 19 inches long, and it has 0.0126 henries of inductance. But I showed you a power supply choke that is less than 4 inches square, and it has 6 henries of inductance. How could something so small have so much more inductance? Well, there's two answers. Number one, there's several hundred turns, not 2,000 probably, but there's many hundreds of turns inside this wrapper here. These windings are wrapped on top of each other. There's many, many layers. It's all one piece of wire wound around and around and around hundreds of times. So to speak, they gang up with each other, and the magnetic field that they all create cuts across all the other ones. There's an inductance magnification going on here. But there's something that's even greater than that going on. Inside the frame of this part, there is laminated iron all throughout here. So the coils are wrapped around the center core of the laminated iron, and magnetic lines of force start circulating on this side and on that side. Notice that the magnetic lines of force are always within laminated iron. The permeability of iron is tremendously higher than air. So the magnetic lines of force are extremely strong, and they exert an extreme amount of influence on the wire, and they create a tremendous amount of counter EMF. Now let's talk about what we really came here to talk about: radio frequency coils. All right, here's a radio frequency coil, but it's a little hard to work with because if you look at it very closely, there's multiple taps on the coil. See them in there? And then there's another coil wrapped around it. So this is actually a form of RF transformer. We don't want to go that far yet, do we? So let's go back to my 17-meter loading coil. Let's see what we could do with this. We come up out of the feed point, and the coil kind of starts bending right about here. So there's one turn, two turns, three turns, plus you have this little loop here that's going to add a little more inductance. So just for the sake of discussion, and it's not too far from the truth, let's say it's a 3-turn coil with 2 inches in diameter and 3.5 inches long. Could we calculate the inductance of that? Well, actually we can. We use a famous formula that you're going to like, especially if you are a resident of the United States of America, because this is your formula. And again, this is not the super easy formula I keep promising. I promise it's coming up. What's neat about this formula, and by the way, I've sourced it from Bill Orr's book. The fact of the matter is, if you look in the Radio Amateur's Handbook, they will give you the same formula. Formula's been around for, 45, 50 years. It is very Americanized, and the reason I say that is it's all done in inches. So don't worry about any weird metric math. You simply plug in the perimeters of your coil, and it spits back a reasonable estimate of the inductance. It's not perfect. It doesn't ask you about the diameter of the wire, but it's adequate for most RF use up to probably several hundred megahertz. So this is a very easy formula to use. We just plug the numbers in. We plug in our diameter of 2 inches. We plug in our length of 3.5 inches and just do the regular old math. We end up with 0.024. But that's not Henry's. We end up with 0.204 microhenries because that is how the formula is designed. Because remember, this is specifically for RF circuitry where we deal in very small inductances. Now, what is 0.204 microhenry? I put commas in just to help you count zeros. So here it would be 1 Henry. Here's 1 millihenry. Here's 1 microhenry. So we have 2/10, well, just a little more than 2/10 of 1 microhenry. You wouldn't think that would be enough to do anything. I will soon show you that in the RF world or radio world, that can do a lot. Now compare it to the solenoid. You see how much more inductance was in the 2,000 turn solenoid. We've learned a lot about coils so far, and I keep breaking my promise about the easy math. Well, the easy math is coming up. What I want to talk about now, we're going to stop talking more or less about inductance. Now we're going to talk about what inductance does, and that is create inductive reactance. See, inductance is a measure of how much your coil resists a change in the current flowing through it. But inductance ignores what role the characteristics of the current play. Remember, we're talking about AC current. So what happens if you change the frequency of the AC current? Inductive reactance is a measure of the total effect on current flow, the role of the inductance, and the role of the applied current. And what that second bullet really means is the role of the frequency of the applied current. That's what's important. Let's take a look at this. This is obviously a very low frequency sine wave. You're familiar with it, and you know that as the current starts to flow, a magnetic field starts to expand, which creates a counter EMF in the wire. And the reason it creates that is, remember, this wire is wrapped in a coil, so any magnetic line of force created anywhere cuts through its own wire that created it. So the counter EMF is happening in the wire. So, okay, let's think about this. It takes a certain amount of time for this to build up. If I increase, let's say this voltage was 5 volts. If I increase this voltage to 100, there's going to be a lot more current, so there's going to be a much stronger counter EMF. But because the increase in the counter EMF matches the increase in the original voltage and current, nothing changes. So generally speaking, the amount of current flowing in the wire doesn't change the inductance or the inductive reactance. But what if I did this? Now, what you're really looking at here, if you count the bumps or the cycles, you're going to find out that the pattern on the bottom is 30 times higher in frequency than the first one. This is a concept that you really want to grasp. I'm going to talk slowly for a reason. If this change in magnetic field is happening 30 times faster, that means when the field builds up, it's doing it 30 times faster. Now, the counter EMF in the wire becomes stronger if the current becomes stronger. But it also becomes stronger if the field expands quicker. So think about it. I increased the frequency of the current, but nothing else. Increasing the frequency has greatly increased the amount of counter EMF. So now the coil is fighting the current a lot harder, and all I did was increase the frequency of the applied current. That is why we say inductive reactance. In other words, the effect of the counter EMF has two ingredients. There is more opposition to current change if you have more inductance in the coil, and there is more opposition to current change if you just increase the frequency of the current's oscillations. So inductive reactance is going to ask you about what's the inductance and what's the frequency, and I'll tell you what my reactance level is at this point. How can we calculate it? I am now going to make good on a promise I made. I'm going to show you this, other than Ohm's law, okay, probably the simplest formula in radio. Don't think it's simple so it's not important. It's actually very important. It's just very simple. This is the formula for inductive reactance. XL is inductive reactance. It's measured in ohms like resistance is. You take 2 times pi, which is 3.1415927, times the frequency in cycles, times the inductance in henries. When you multiply all that out, the result is the inductive reactance in ohms. And what you should be able to tell here is this never changes, but these two do. If either one increases, the reactance increases. If you increase the frequency, or if you increase the inductance of the coil, the reactance is going to go higher. Now, here we go. What do you suppose the inductive reactance of my 3-turn coil is? Well, let's say we were to use it at the power line frequency of 60 hertz. Let's plug the numbers in. 2 times 3.14 times 60 cycles times 0.00000204 henries. Well, you know as well as I do, that's 80 microohms of resistance, or inductive reactance. Well, 80 microohms is nothing. You might as well just say, okay, your coil's not even there, Mark. Move up to the AM broadcast band, right in the middle of the band, 10 or 1000 on your dial. That's 1 megahertz, 1 million cycles per second. It's still, my coil is a nothing. Nobody cares that it's there. Go up to the 17 meter band. Look at this. We got 23 ohms of reactance. When we talk about capacitive reactance and impedance, you're going to find out that in an RF circuit, 23 ohms is actually a significant number. Of course, on 2 meters, it gets even higher. All right, now let's go back and think about that solenoid. What do you suppose the solenoid will do? Well, at 60 cycles, we already have almost 5 ohms. It's not really much, doesn't really matter, but it's something. In the middle of the AM broadcast band at only 1 megahertz, look at what we have. Why is it so much higher? Well, it's because you didn't increase frequency or inductance over what's up here. You increased them both. They're both higher. So the point here is when you do the F times L, if either one of them starts to get big, that's one thing. When one of them is already big and the other one starts to get big, you start to get numbers like this. 1.4 million ohms? Are you kidding? On 2 meters, it's 10 times, 11 times worse. So take a look at those numbers. And you can see why I introduced you to the solenoid. You can also tell why the solenoid coil, with all that reactance, is worthless in radio. What are you going to do with a 11 million ohm reactance? You're never going to use that anywhere. Now, in case you didn't catch it, let me ask you this. What happens? Because remember, this is a 4-part multiplication problem. 2 times pi times whatever F is times whatever L is. What happens if any of these entries is 0? Let's say I've got a very high frequency, millions and millions and millions and millions of hertz, but I have 0 inductance. I don't care how high in frequency you go, if you have no inductance, you have no inductive reactance whatsoever, it's just not there. If you have a tremendous amount of inductance, but your frequency is 0, in other words, it's DC current, you have essentially no inductance. You do have an inductive kick when you turn the power on and when you turn it off. Other than that, with DC, inductors have no effect. I hope that 25 minutes was worth it to you. by all means, watch it as many times as you have to. If I've not presented it in a way that clicks in your head, I urge you to grab any of the textbooks shown on the screen. Well, not the dictionary. I guess that one doesn't really belong up there. I mean, it does, but it's especially entry 4 and entry 5. Those are the best ones when you're beginning. Although I'm not discouraging you from John Krause's book either. In the next couple of videos, I'll be doing capacitors and capacitive reactance. Then I'll move into impedance. And then you can go have fun with modulation and radio components and all that other stuff. What now we're in the middle of is the foundational elements of radio. Again, thanks for watching, and I guess I'll see you next time.